Is it fine?
Not yet.
Oh, it should be live. Okay, I'm starting. Is it fine?
No signal now.
Come on live.
No, it's here now.
Say
something.
Okay, we're finishing with the metric stuff on manifolds. Okay, so last time I introduced the metric tensor, but I didn't see what's about. It's in metric on finite dimensional real vector spaces like 2, 3-dimensional plane or space. They measure lengths and angles between vectors, and on manifolds, you can say they measure something on vector fields, but they usually, if you restrict them locally to a point, they measure distances and angles between tangent vectors. But because we are not going to do tangent vectors, I'm not going to be specific about that. But something interesting is that they can be used to define measures of the whole space. So that's what I will define and do a simple calculation, how to measure areas and volumes on. So let's do some definition. I will do two definitions in one place. So let M G be a Riemannian manifold. So smooth manifold is metric. Let it be compact. I said compact sets few time ago, but it's closed and bounded set. Something like a sphere or a closed ball, something like that. So and also oriented, compact, oriented, Riemannian manifold of dimension D. Manifold of dimension D. So I will define three things. So first, with volume form, so okay, the volume form it will be vol like previous time. So first, the measure of M. So this is length, area, volume. For D equals 1, 2, or 3. The measure of M is defined as, so let's call it mu of M is integral over M of the volume form of M. Maybe with respect to G, but usually only vol. I will write only the symbol vol. 2, so this is without any arguments. We can have a Riemann integral, which is a little bit more generalized. Something that I want to say I will not write, but because the volume form depends on the orientation, if I change the orientation of M, the volume form also changes sign, but the whole result is 2 minus signs. So it's the same. So this thing is always positive. It's always positive. And second, the Riemann integral of function f is defined is, I don't know how to call it, maybe integral of f, I don't know, is integral is usually taught, is usually students are taught that functions are integrated, but you cannot integrate function, you can integrate volume forms, you can integrate top dimensional forms. So in 1D, this will be f times dx, volume will be dx. So, okay, in 1D, this is I of f, and m is the interval AB. E of f is integral of a to b f dx. So this is a generalization. In 2D, we have dx dy, and this should be two-dimensional interval, and so on. But this works for curved manifolds as well. And 3, the inner product of two forms, here P is from 0 to D, is defined this way. So it's omega eta. I usually put P, not always, but I will put P to, because it's different for different forms. And by definition, this is the integral. So this is the Riemann integral of the metric tensor of these things. So metric tensor returns the function. And if we expand, this is the same as integral over m of gp omega, gp star omega eta, wedge the volume form. Maybe not. When you multiply a function with a form, it's the same as wedging it, so I can write without a wedge. Doesn't matter. Note that if f is the constant one, the integral of 1 is the area, the measure. Okay. I will do measure of parts of a sphere and the whole sphere as well. So this is area of sphere sectors and the whole sphere as an example. Okay. So example. So 2 m is S2R. So this is the set of points such that x squared plus y squared plus z squared is r squared. I will do the length of the surface area of a sphere, because if I do the volume of a ball, it will be much bigger computation. So I want to want. I will put small one, not to confuse somebody. Okay. So, and with standard orientation, so induced orientations and metric with induced orientation and metric from R3. Okay, so in spherical coordinates, so the spherical coordinates look like that. X is R sine cosine, sorry. Small r. R cosine theta cosine phi. Y is R sine theta cosine phi. Sorry, cosine theta sine phi. Cosine theta sine phi. And Z is R sine theta. And here theta is from 0 to pi and phi is from 0 to 2 pi. This is not a full parameterization, but only of the without the Greenwich meridian, but it's fine enough to finite measures, because if you remove a one-dimensional part from a two-dimensional, you don't change the volume, the area. Anyway, so the volume form, we computed it previously when R is 1. When we have R here, because it's two-dimensional, we have one coefficient R. So this is with R sine theta, d theta, which d phi. You agree with that? This was last time for a sphere with radius 1. Okay, and so let's do some image. So we have some sphere. I will do spherical quadrilateral. I use this for some examples in my code, so that's why I want to show that. And I have something like that. So call this this, for example, phi 1, phi 2, theta 1, theta 2, is it right? Yes, theta 2, is it right? Yes. Okay, and we are in this region here. So, so we are calculating the area of a spherical quadrilateral of this spherical. So here theta is in theta 1, theta 2, and phi is in phi 1, phi 2. Okay. So what do we have? So the area A, call it A. So A is integral over M. So this will be in spherical coordinates. We have this integral from theta 1, theta 2 times phi 1, phi 2. So this is the parameterization of this small quadrilateral. And r squared sine theta d theta which d phi. I didn't explain that previously, but we can use Fubini's theorem. Integral over a rectangle can be separated into as a product of two integrals. And first of all, we have r squared goes outside, and then we have, so here we are using Fubini. Integral, you know Fubini's theorem? Okay. Theta 1, theta 2, sine theta d theta times, so this integral, integral phi 1, phi 2 d phi. So we have r squared. This will be cosine theta with -1, so this will be cosine theta 1 minus cosine theta 2. And here we have phi 2 minus phi 1. Okay. Total area, so total area of a disk, total area of S2R is, so let's call this, is r squared cosine of 0, so the whole interval here, 0 to pi and 0 to pi, minus cosine pi times 2 pi minus 0. And this is 2, this is 2 pi, it becomes 4 pi r squared, which you should know. Okay. So the total area will be when we span the whole interval, so both theta and pi. Okay. If we get some Riemann integral, we will be integrating function f here of theta and phi. So we have some multiplication here with some function as well. And the rest is integration. We also can find lengths and things like that, but let's keep that. So because I have spherical examples in my code for the method, and because the combinatorial mesh calculus formulation require to know the measures of these cells, this is how they are calculated. So I can calculate areas like this, and I calculate lengths from the volume form of one-dimensional manifold. But I'm not going to do that. Okay. So now I define the inner product. I don't have some interesting example of inner product. This will be used for weak formulations for the model, the transport phenomenon. Let's define one more operation, the codifferential. So let NG be a compact oriented Riemannian manifold. This is the dimension of M. So, and P is positive integer from 1 to d. So we have first consider the space omega 0 bullet m. So this is all the forms that are 0 on the boundary. So 0 omega is a form such that trace of omega is 0. This is the same space if we have manifold without boundary, but usually we have boundaries. So the codifferential is defined by codifferential delta p from omega 0 p m to omega 0 p minus 1 m is the what's called the adjoint of d when restricted to omega 0 omega 0. So this is adjoint of dp minus 1. So that means that E for any omega in omega 0 pm and eta in omega 0 p minus 1 m, we have the following. So delta star, no, how do I call it? No, I think I use the dp star. So in the paper, dp star of omega with eta on p minus 1 forms is the same as omega d eta. This is on p forms. Now I state the proposition. It's proven in the. It's very short, but I don't want to prove it. It's proven in the preprint. So we'll have the following. dp star satisfies the following. Satisfies the following. So maybe d star on. So d star d minus p composed with star p is the same as minus 1 to the power of p plus 1 star p plus 1 composed with dp. Let me write this in a diagram. So we have things like omega 0 going. So we start from omega p and we go to omega maybe 0. with data zeroed the boundary. So usually with these operators, there are problems when you apply them on the boundary, but we try to not apply them on the boundary for that reason. Omega d minus m, and here we have d minus star, and this is star p. This is omega d minus p minus 1. And here we have with dp omega p plus 1. And here we apply minus 1 to the power of p plus 1 star p plus 1. Sorry, I have to write star like that. So we have this diagram here. I write it in this way because this is true also for in the discrete world, and in the continuous world, the Hodge stars are invertible, and we can write that also as d minus p star is minus 1 to the power of p plus 1 star p to the minus 1. No, sorry, star p will be on the right. Star p plus 1 composed with dp composed with star p to the minus 1. And this is minus 1 to the power of p times dp. So this will be minus 1 p plus 1 plus p d minus p star composed with d composed with star d minus p. So this to the minus 1 is this times minus 1 to the power of this. Let's do some example. For instance, example in D, let be 3, P is 1, no, P is 2. So D1 star, this is will be the divergence. So D1 star will be minus 1 to 2 plus 1 plus 2, 3 minus 2 star 2 plus 1. Okay, write it this is 3 minus 2, 2 plus 1. D2 star 3 minus 2. And so we have, this will be D1 star is minus 1, because this is even and this is odd, minus star 3 composed with D2 composed with star 1. And let's see what it's so about. So D1 star of fx dx plus fy dy plus f z dz will be minus star 3 of, so the star 1 makes dx to d, so this is star 3 of d2, and then this will be fx dy dz, fx dy dz plus fy dx dz wedge dx plus fz dx wedge dy, fx dx wedge dy. This is minus star 3. And this last time we saw like divergence. So this will be minus divergence. So this will be minus df x dx plus df y dy plus df z dz dx wedge dy wedge dz. So this is computation from few lectures ago, I think, when I introduced the exterior derivative. And the star 3 just removes this part here, so this becomes minus the fx dx plus dfy dy plus df z dz. And what is this? Yeah, this is like divergence. This is minus the divergence of fx ddx plus fy ddy plus fz ddz. And this can be written as minus the divergence. This is the whole, I'll call it. So maybe I should start here with omega, d1 of omega. And this will be the minus the divergence of the sharp of, no, the flat of omega. Is that right? No, the sharp. The divergence of the sharp of omega. So what we saw is that the sharp operator was the inverse metric in some sense. I introduced it last time. So we see that d1 omega, d1 is minus divergence composed with sharp. And similar things hold for d2 and d3, but I'm not going to do that. So d2 will be, I'm not sure, the sign plus minus something related. So d2 will be related to gradient, which is related to d0. This is related to d1, and this is related to d2, something like that. It can be made more precise with sharp and flat operators and with the signs, but I want to just get the idea. So we can go up in the dimensions and go down. And in these guys, maybe you can say that we have only divergence current gradient, but these operators are uniformly defined in all dimensions. Okay. Okay, so now let's go to a bit of physics. The transport phenomena. Can I erase the board? So we have the whole calculus in some sense set up to formulate our. So the transport phenomena in exterior calculus formulation, and the benefit over, for me, there are two benefits over to me over vector calculus. First, all the quantities live in their natural domain, and second, the formulation with spherical calculus is directly translatable to combinatorial mesh calculus. Okay, so the transport phenomena with exterior calculus. So let's fix the setup. So we have M, so D spatial dimension, omega, M is D-dimensional, maybe with G. Compact oriented Riemannian manifold. So this integer, of course. Riemannian manifold. And this is by assumption is with boundary. For me, all manifolds have boundary. Okay, I can write it explicitly with boundary. With maybe non-empty boundary. Okay, with boundary. So this is spatial domain. Spatial domain of a solid body, probably. Okay, solid body. So I have this here, one maybe, no, with bullet points. We have T0 some real number, and E is T0, maybe not to infinity, but for me it's easier to fix infinity. This is time interval for the problem. The phenomenon. Okay. And that's the initial setup. So I think with boundary, let's call it, sorry, partial M. Yeah, it's obviously partial M always. So and so we are studying the transport of some quantity inside some extensive quantity. Yeah. So this may be energy, volume, charge, mass, charge. inside M. Inside M in the interval I in the interval. Okay. So this is the idea. Now let's do quantitative set description. So we have the following variable quantities. So quantities. So first we start with the amount. So this is the extensive quantity. Which is a amount Q, which is a deform. No, sorry. It's a function from the interval to deforms. So this is a smooth function. We start in an interval, and the result is a deform. So this is a dimension, a physical dimension, physical sum. It's not clear initially of some physical dimension X. So that such that if T1 and T2 are in I, and V is a submanifold of M, we have that the integral over T0, T1 of V. So this is, so this thing here, because this is a tree form, we can integrate it without dx, and here we have dt. We need dt. This is amount, total amount I'm not sorry, I did some mistake here. No, it should be that way, but let me see what that means. Oh yeah, sorry, not this one, not integral. The integral of q dv at times, so q at times t1 minus q at t0 is the amount difference so maybe no, I just if t is in I, sorry, q of t, integral of vq is the total total amount in volume V at moment t. So we have some we have, for example, energy is a three-form, dynamic three-form, and at point t1 integrate, we find how much energy we have in some volume. We also have flow rate. So what's usually called flux. So usually energy is energy density or mass given by mass density. Here it's given as a form, not as a density. So densities are defined at points, but this is defined. It's expected to be integrated on volumes. So this is the dimension is x. For example, x is energy or something like that. It is not x time length minus third. It's not the density. It's an absolute physical dimension. We have flow rate. F, I call it Q, which is d minus 1 form. Q is of dimension power. So it's not power, but amount per unit time. So measures outflow. So measures net flow through a surface. D minus 1 dimensional surface. Dimensional surface. So I make it this picture. I will talk about relative orientations when I talk about meshes, so I'm not going in details about that. But we have some surface here, and it has some volumes around it. So this is S, and this is V plus and V minus. And there is some transport from here to here through S and from here to here to S. So this is, for example, QV plus. So this is QV minus to V plus, and this is QV plus to V minus. And so Q is by definition, Q at S is Q from V plus to V minus Q from V minus to V plus. So we have some flow we have flow in both directions, and we measure the difference in flow rates. So the net flow through surface through S in T1, T2, this is subset of I, is integral from T1 to T2 and from So we are doing double integral. We have to put dt because it's a function with respect to time, but with respect to space, it's already it's a d minus 1 form. So it's already d minus 1 form. So it has dx and dy included in it. Again, in classical vector calculus, this will be divided by area because it will be density, but here is not divided. This is just how much energy passes per unit time, for example. Okay. We also have the flow. I call it internal production rate. This is usually a reactive term. Internal production rate, which is also a reaction term. And this is, I know that usually people use R in fluid dynamics, things like that, but in most mathematics formulations of heat equation, usually the right side function from I. So always it's dynamic. The process is dynamic. For steady state, we do without interval. 2 omega d m. It's a dimension again. So the amount divided by t to the minus 1. So F measures internal production inside in a volume. So if V is the manifold, so the dimension of it's a subregion. It's a subregion. It's a subregion. It's a subregion. And we have some interval. T1, T2 is subinterval I. Then the total internal production in volume in V for the interval, for the time interval. Maybe I call it volume here, volume V. Be more explicit. Time interval T0, T1, T2, sorry, is integral over T0, T1 over V of Q dt. So we have production rate, for example, energy per second, a joule per second. And when we integrate with the time, we will get energy. And the Q integrated doesn't introduce any new dimensions. So this will be the total production rate in interval. For example, we have a heat source, and inside small volume, we measure how much from time 0 to time 1 is produced inside. Okay. And so with these three, we can formulate conservation or continuity wall, however go it. So continuity wall or conservation. So let's write it in words and then in formulas. So let V in M is and T0, T1 is subset of I of the interval. Then total production. So no energy, not energy, amount difference in V between moments T0 and T1 equals to, so we measured some energy in some volume with T2 times, and this is the production in energy, so total production in V for interval T0, T1, T2, sorry, minus what goes outside, what's leave, what minus total outflow through the boundary of it, through dV for the interval T1, T2. This is in words, and this is the same as the integral of Q Q1, not the integral, sorry. Integral of over V of Q at T1 minus integral of V of Q T T2 and T1. So this is the first term. The second is on the left side. The first term on the right is integral over T1, T2 of F dt, sorry, minus integral. So this is the total production, and the outflow is T1, T2, and of the boundary of Q. And this is the T. And let's write this in, so this is in integral form. So this is what's actually measured, but with the help of Stokes Theorem, we can write this in a differential form. So because so integral of V T2 minus integral of V QT1 is the same as d dt of integral Q of this thing here. Not d dt. Let me. Sorry, the q dt. This here. something like that. This is the same, and the integral of t1, t2 of dv of q, the whole respect to dt, is integral of t1, t2 v dq, d minus 1q dt. And so what we get is that the integral of t1, t2 of v, and here we have dq dt equals, and the whole is the same as integral over t1, t2, integral v, f minus d2, d minus 1 of q, and the whole dt. And we can remove the integrals. And so we have dq, because this is true for all subvolumes and all intervals, this means that dq dt is f minus dd minus 1 q. Okay, let's make a break. So this is differential form. Of continuity law, of conservation law. The similar similar argument is used in vector calculus, but there the operators are different. It's not D, it's divergence. It's not a form, it's a density. This is also density. So write it, and in vector calculus we have, let's write it with tilde, dq dt is f tilde. We have, let's write it with tilde, dq dt is f tilde minus divergence of q tilde. Something like that it looks. And these are density forms of these operators. Okay. Any questions?
Language codification, I would call the integral form conservation, and that differential is not conservation.
Continuity, maybe. Okay. Okay, continuity. Continuity. I know that.
I mean, you need to have a very strict conditions in order to go from the integral to the differential.
Oh, everything is smooth. Okay. Yeah. Integration is more general because, okay, we're looking on smooth manifolds and there everything is differentiable, but in reality, we cannot always remove, we cannot do from this to this very often. Okay, I'm finishing this stream and make the break.